Hi everyone, welcome to the online lecture series on VLSI testing and design for testability. I am Maragadraj, Assistant Professor of EC Department, and the subject code for this particular course is CEC362. Hi students, I hope everyone is well. So let us go to the lecture. So till now in this particular semester we have completed 3 units, that is Unit 1 Test Requirements and Metrics, Unit 2 Scan Design and BIST, Unit 3 Memory Test and Test Interfaces. So the remaining 2 units we are having the Unit 4 Design Considerations and Power Management during Test, and Unit 5 Analog Test. Unit 4 will be covered by me during the class hours itself. So yeah, Unit 4 will be most probably like a discussion. So I'll be discussing more of these topics in the classes itself. Moving over to the Unit 5. The Unit 5 topic is analog test. As the name mentioned, analog test, this particular topic discusses about the test requirements and the testing methods of analog ICs and analog and mixed signal ICs also. If you look at the syllabus more closely, what are the topics that we are having? Test requirements, DFT methods, BIST methods, test versus measurement. So up until this particular topic, what are the types of requirements that you need to test a analog IC? So this is different. Okay, so analog, basically the nature of the signal differs. It differs from digital part where we have only two states, that is 0 and 1. So it is more or less easier because we have only two states, that is true and false. Here the test requirements and design for testability, it should depend upon the type of measurement that you take from a analog device. Being a non-linear devices, the analog circuits, they give a different type of outputs that change very different from that of a digital circuit. So that is the major one of the major challenges in testing an analog circuit. And after that, defect tests versus performance test. Tests for specific modules such as PLL, phase lock loops, IOs, and more importantly ADC and DAC. As you already know, ADC and DAC, they refer to analog to digital converter and digital to analog converters, which are an integral part of an IC that deals with analog signals. Okay, and at last there is a RF test requirements. RF test requirements deals with the high frequency, that is the frequency response part of the analog ICs. Okay, so let us go to the course. Okay, please wait a second. Okay, welcome back. So let us move into the syllabus that we are dealing with. So as I told you before, this particular chapter, it deals with analog and mixed signal testing. Okay, so what is this? What are we going to learn about in this particular unit? First thing, here we are going to see about what is analog and mixed signal circuits, what are the failure modes and fault models that are available for this analog and mixed signal, and what are the different parameters that are available or that can be focused for testing these types of ICs. And then we can discuss about the various testing approaches that are available for analog to digital and digital to analog code converters. And at last I'll give you an overview of IEEE standard that is available for testing these types of circuits. So next, analog circuit properties. Before we go into the analog circuit properties, let us go through a brief history of the inherent nature of analog signals first. So what is analog? most of the signals or almost all of the signals that are available in nature is analog in nature, be it a sound or that the signal that we receive from any type of sensor, this everything that we get it as analog signal. So how do we convert it into digital? We need code converters for quantizing and converting these signals into a digital stream. So what are the basic analog circuit properties? First, it is a continuous signal that you already know. It is a signal that is continuous with respect to time, and there is a very large varieties of circuits that are available. It starts with a diode, and then it moves from diode to we got UJT, BJT, FET, MOSFET, and then still we can move on to LIC, where we have a variety of op amps, and then we can move on to various types of applications such as multivibrators and PLLs, oscillators, etc., etc. So there is a very large variety of circuits that is unique in each of their mode of operation. Next, non-linear characteristics. So being an amplifier, so it is a non-linear device. And then feedback ambiguity. When you go for a more complex circuits, we have two different types of feedback, such as negative feedback and positive feedback, and we have circuits that need negative feedback to gather more stability and more, and we for having a reliable gain. And also on the other hand, you have oscillators that need positive feedback that for satisfying the Barkhausen criterion and for operating in that manner. And then if you go for feedback, there is a very complicated cause effect relationship. Let me explain it later with an example. Okay. And then here the analog circuits, they do not have a suitable fault model for that covers all the circuits. For example, you may have a type of fault model for a diode that does not apply for a BJT. So if you have something for BJT, does not apply for op amp. So there is a absence of suitable fault model that is universal for all these types of analog circuits. And the source, if you do not have any fault model, then how will you find a particular fault in a IC? So this is how the challenge this is where the challenge gets more and more larger, or it gets more interesting, because if you want to uh, gather the fault in these types of circuits without any particular fault model, then the circuits or the devices that you need to check the ICs, they must have very accurate operation. Next, here I have shown the properties of continuous signal, that is a difference between a digital signal and analog signal. So if you have a digital signal, naturally you have a rise time, fall time, and there is a latency between the rise time and fall time. So you have V in high, V in low, V output high, V output low. So you have rise time for fall time, that the latency between the rise time and fall time, we normally say it as a propagation delay. And then the noise margin is high or low depending upon the application. Here, what are the parameters that define an analog signal? The first thing, what is the type of signal that we use? It can either be a voltage source or a current source. Next, the slew rate, the rate of change of the particular signal with respect to time, and this is the overshoot that you do have studied this in control system. And then this is the damping factor. Damping factor is nothing but when you provide a signal to a system initially, there is a particular time for the signal signal strength to get established within the particular system. So first, initially when you give the input goes higher than the particular nominal rate, that you tell it as peak overshoot, and after a particular time it gets stabilized in this particular time, that is mentioned at t settle. After the settling time only, the particular the stimulus that you give, either it can either be voltage or current. After this particular t settle time only, the this value will be established within the circuit. The damping factor decides the t settling time, and then we have the frequency of operation and we have the bandwidth. Next, what is digital circuit and what is analog circuit? Here in digital circuit, we have two basic types of operation. One is called static, and the second is dynamic logic. And depending upon the structure of transistors or the mode of construction of the IC, we can differentiate it as gates or PLA or memory. Either it can be RAM, ROM, etc. If you go for analog circuits, the principal modes of operation, it can be either in current mode or voltage mode, or it can be in switching capacitance. Depending upon the internal structure of the IC, it can either be an amplifier or a multiplier, rectifier or a resonator. So if you see, naturally the analog circuits have a more variety than the digital circuits. So what is meant by non-linear characteristics? Because this is the one thing that causes a very major challenge for testing analog circuits. So if you look at a diode, this is the VI current characteristics, VI characteristics, voltage to current. So here it does not go linearly. The diode does not conduct until it reaches a threshold voltage, and after this threshold voltage it goes linearly. So if you take this whole period of operation, it is non-linear. Similarly, if you take the case of a MOSFET, it has three regions of operation: cutoff, linear and saturation region. And the current, ID current, the equation for ID current is different in each case. For example, in cutoff region, the drain current, it should be 0. In linear region, it will be in it has a different equation, and the equation shown here, it is the equation of the drain current and the saturation region. So we have three different equations for a single device at various times of operation. So this poses a greater challenge, because we don't have a universal expression for where you can apply your assumptions and to derive a solution. Next, what are the causes or what are the challenges that is posed by feedback? So you already know feedback. We need two different types of feedback, that is positive and negative for applications. So if you have a feedback, the problem is you are taking a part of the output. If you consider this particular operation, a particular op-amp circuit, you are taking a part of the output and feeding it back to the input. So if there is there is a fault in this particular capacitor, we will not be able to identify the fault in the capacitor until we derive the particular expression for this feedback loop, or else we will not be able to arrive at or identify this particular fault. Next, complicated cause-effect relationship. We have different modes of circuits in analog. voltage mode, current mode, and switched capacitance mode. And for each for a particular single type of circuit, if the source is voltage, you have a different set of equations. And then similarly for the same circuit, if you have a current source, you have a different set of equations. So here, in such a scenario, it is very difficult for the designer to arrive the cause of the fault. Because consider this, yeah, for example, consider your smartphone. So your smartphone has a IC inside it. Your smartphone is capable of recording your heartbeat. That is, you are having a sensor. The sensor is going to read your analog signal, and that analog signal must be converted into digital for further processing. So in this case, your heartbeat or your pulse must be detected and sent to the IC. So inside the IC, you will naturally have analog to digital converter for converting this data. So your smartphone IC is a mixed or analog and mixed signal IC. So that it can either be a voltage source or a current source. So at that time, it becomes very challenging for the designer to check the faults. Next, what are the advantages of in detecting faults in digital ICs? For digital ICs, first advantage is that you are having a logic. That is, it should be, the logic is either it is 0 or it is 1. Depending upon logic, you are creating a fault model. That fault model depends upon the type of circuit. For example, you have combinational circuit or sequential circuit or memory circuits. Depending upon that mode of the mode or the subsystem, you are choosing any particular type of fault model. For example, if you have these three, stuck at 0, stuck at 1, stuck open, short open, these types of first three types of faults, they are normally used for combinational circuits alone. Next, if you go for memory faults, in this memory faults you have different types. For identifying the fault in either it can be RAM or ROM, and then you go for further step. You are going for applying these fault models in PLA. So these are the fault models that are established and checked, and it can be applied for all the circuits and all the type of digital circuits wherever necessary. So digital faults is easier to identify because we have a standard fault model. What is the challenge in analog faults? Number one, there is no good fault model because it is not generally accepted by the or it is not generally standardized in the industry. It is because the analog circuits varies between different manufacturers. One type of manufacturer, they may use voltage mode circuits predominantly. Another type of manufacturer or for another type of application, they may use predominantly current mode. So we can't standardize we are not able to standardize the common fault model for each circuit because the types of circuit available in analog ICs is very large. So this is the one of the major drawbacks in analog faults. Okay, thank you.